All right, so what we're going to do to figure out how Q-learning works is we're going to think about what it means to estimate this Q function from transitions. So let's just remember this is the form of the Q equation that we've been talking about. And we can't do this. We can't solve this because we don't have access to R and T. All we have access to are transitions.
Oh, so this is really, I guess. I mean, I guess you said this before, but when you write out this equation, it really jumps out at me. This is the difference between what I was talking about, solving MDPs, and reinforcement learning. In solving MDPs, we had R and we had T, and now we don't have them, so we have to come up with some other way to solve these kinds of equations.
That's right.
Okay. So if we did have R and T, then we could solve this?
Yeah, this is, I mean, the same things that you talked about, value iteration and policy iteration, that can be formulated in terms of Q. So this is easy to do. Well, it's polynomial to do if we have access to T and R. But again, in the learning scenario, we don't have the model. What we have are transitions.
Okay.
So here's how we're going to use transitions. This is what a transition is. We observed that we were in some state S of the MDP, and then action A was chosen somehow. And then a transition happens. We land in a state. We get the reward for landing in that state, and we find out what state we're in. So that's the transition. And what are we going to do with it? Well, what we're going to do is imagine that we've got an estimate of the Q function, Q hat, and we're going to update it as follows. Here's how we're going to use all these quantities from the transition. We're going to take the state and action that we just experienced, and we're going to change it. We're going to update it. We're going to move a little bit, alpha. This is called a learning rate. We're going to move a little bit in the direction of the immediate reward plus the discounted estimated value of the next state. So we're going to take our estimate Q hat. We're going to take the state that we end up in as prime. We're going to look at all the different actions we could take from there and take the maximum. So this together is kind of an estimate of the utility, right?
Mm-hmm.
And this is the utility of the state that we're going to. This altogether is the utility of the state that we were in, this state S. So this is kind of the utility of the state that we're landing in S prime, and this altogether is related to the utility of the state, right? You can see that it's related in that we've got the immediate reward, which kind of matches to this. We've got the discounting. We don't have the sum over transitions, but we do have the max A and the lookup in the Q function. All right, so this is the Q-learning equation. All right, let me just say a little bit more about this alpha arrow notation, which I really like, but is not all that standard. So when I write, something like V gets with an alpha x, what we mean is that we're moving alpha of the way from the current value of V towards x, which can be written this way, that V gets 1 minus alpha of V plus alpha of x. And so in particular, if you think about this as, so if alpha is 0, that's sort of a learning rate of 0. It shouldn't learn at all. And in fact, if you set alpha to 0 here, it's going to zero out x, and it's going to only assign v to v, so nothing's going to change. So a learning rate of 0 corresponds to no learning. And if we set alpha to 1, that's like full learning. So we forget everything that we knew, and we just jump to the new value. And that's what happens here, that 1 minus alpha is 0, so the v goes away, and we just get x assigned to v. Does that make sense?
That does make sense. And if alpha were in between 0 and 1, like 1/2, you're basically making v the average of the old value of v and the new value x that you see.